What we have done in the last lecture is that we have completed discussion on supervised, semi-supervised and unsupervised words and disambiguation. We also mentioned that we will briefly touch upon resource constraint words and disambiguation. Unsupervised words and disambiguation was a method to do words and disambiguation when one does not have training corpus. Training corpus is a costly resource which takes time, money and manpower to create. Now, there are many languages which are resource constrained. They do not have lots of training corpus. They do not have other NLP tools, techniques and so on. So, we have investigated the problem of resource constrained words and disambiguation at IIT Bombay, and I would like to briefly discuss this. So, this kind of work is called parameter projection and iterative words and disambiguation. Parameter projection is based on making use of multilingual word nets where synsets are aligned, and these ideas are useful for language and domain adaptation. The meaning of language and domain adaptation is that if we have words and disambiguation in one language, then the work can be reused for another language. Similarly, if we have words and disambiguation for one domain, say tourism, we can reuse the work for another domain, say health. So, language and domain adaptation is a very important idea, and I would like to present a matrix which is drawn on the paper to see the immense potential of the work. So, here is a matrix where we have domain and language. So, we can have things like tourism, health, sports, economics and so on. And here we have languages, let us say English, Hindi, Marathi, French and so on. So, if we have domain and language adaptation, so suppose we have created a WSD system here. This is the WSD system built for Hindi and tourism. Now, is it possible to make use of this work and create words and disambiguation for, let us say, Marathi and health here? Can we do this? So, we adapt this system for tourism built for Hindi and create a system for Marathi and health. From this, let us say, can we go to a system for English and economics. So, this is a very interesting possibility, just like a virus or a team of ants produces a colony spreading from a center and creating the colony around it. Similarly, our vision is that we have a words and disambiguation for one language and one domain, and it spreads around for different languages and domains. This is the idea. So, can we do this? Now, looking at the slides, we have done a number of interesting work on multilingual words and disambiguation. So, they were presented in top forum like Polling, ACL, Empirical Methods in Natural Language Processing, Global WordNet Conference and so on. So, we proceed to discuss the techniques. Before that, the motivation. As has been said, parallel corpora, word nets and sense annotated corpora are scarce resources. The challenges are lack of resources, multiplicity of Indian languages. So, can we do annotation work in one language and find ways of reusing it for other languages? Can a more resource fortunate language help a less resource fortunate language? So, the introduction is that we would like to perform WSD in a multilingual setting involving Hindi, Marathi, Bengali and Tamil. The wordnet and sensemark corpora of Hindi are used for all these languages. The methodology rests on a novel multilingual dictionary framework. Parameters are projected from Hindi to other languages. The domains of interest are tourism and health. So, this line of work derives its base ideas and inspiration from well-known algorithms like Lesk algorithm, Walker algorithm, conceptual density, page rank based algorithm, which are knowledge based approaches. Then SVM, k nearest neighborhood, decision list, which are based on supervised approaches. It also draws from semi-supervised, unsupervised approaches like hyperlex and decision lists. And hybrid approaches are the motivation for our work. Structural semantic interconnections, combine more than one knowledge resource, wordnet as well as small amount of tagged corpus. So, this is suitable for broad coverage. Now, here is the punchline of the work. No single existing solution to worsen disambiguation completely meets our requirements of multilinguality, high domain accuracy and good performance in the face of not so large annotated corpora. So, before we begin our discussion, we first identify the crucial parameters for worsen disambiguation. As has been said many times, when a word is disambiguated, the clues come from the neighboring words. So, that naturally creates a setting for parameters of worsen disambiguation. Clearly, if we are using training corpus, then the sense of the word which occurs most frequently will be a very important parameter for disambiguation. The relationship of this word with the words in the neighboring context and their senses is also very important. So, these considerations give rise to a number of parameters which are shown on the slide. Here is a motivating example. The river flows through this region to meet the sea. So, the target word for disambiguation is sea. The meanings of sea are given here as obtained from the English wordnet. Sea as a noun, a division of an ocean or a large body of salt water partially enclosed by land. Sea can mean anything apparently limitless in quantity or volume. This is a metaphorical usage. Another meaning of sea is turbulent water with swells of considerable size. Heavy seas is an example. So, what we see is that there are two so called physical senses of sea in the sense of water body and a metaphorical sense of anything limitless in quantity or volume. Now, we will see that domain specific distributions form an important component of the parameters for WSD. In the tourism domain, the water body sense is more prevalent than the other senses. Domain specific sense distribution information should be harnessed in our algorithm. Okay. So, this is our first parameter coming from the corpus, sensemark corpus. Dominance of senses in a domain, that is a very important parameter. Place, country, city, area, flora, fauna, mode of transport, fine arts are dominant senses in the tourism domain. So, what we see is that a synset node in the wordnet hypernymy hierarchy is called dominant if the synsets in the subtree below the synset are frequently occurring in the domain corpus. So, domination is determined not only by the frequency of a particular sense, but also its children in the hypernymy hierarchy, its descendants in the hypernymy hierarchy. So, a sense being dominant is conditioned on pretty stringent criteria. its own frequency and also its descendant's frequency. A sense which belongs to the subtree of a dominant sense should be given a higher score than the other senses. Corpus co-occurrence statistics is very important. Co-occurring monosemous and or already disambiguated words in the context help in disambiguation. For example, the frequency of co-occurrence of river, which is monosemous, with water body sense of sea is high. Okay. So, the sea also has this metaphorical sense of something limitless, but that will not have high co-occurrence, that sense will not have high co-occurrence with river. River is a monosemous word, by the way. Semantic distance is the shortest path length between two synsets in the wordnet graph. An edge on this shortest path can be any semantic relation. Then there is this notion of conceptual distance between noun synsets. The distance between two senses S1 and S2 is defined as the length of the path between the senses S1 and S2 in the wordnet hierarchy divided by the height of the lowest common ancestor of senses S1 and S2 in the wordnet hierarchy. So, this particular point was discussed when we mentioned the conceptual density based words and disambiguation algorithm. So, the distance between two senses is important, but the distance has to be seen in the context of how general the senses are. We had mentioned before that the distance between a cat and dog, which are children of the animal node, is 2. Okay. Cat and dog are siblings of each other. Similarly, the concepts abstract and concrete are also siblings of each other, but they come very high in the conceptual hierarchy. Clearly, the distance, the quote unquote distance between abstract and concrete, which are very large concepts, even though the length is 2 between them, that is not representative of the actual conceptual distance between abstract and concrete. Cat and dog are very similar, but abstract and concrete are two large conceptual worlds. They are very distant from each other in terms of semantics and conceptual categorization. Okay. So, the height of those concepts in the conceptual hierarchy is important. There are other parameters which are there, but the main parameters for words and disambiguation are wordnet dependent parameters, belongingness to dominant concept, conceptual distance and semantic distance. They come from the wordnet, and corpus dependent parameters are sense distributions and corpus co-occurrence distribution. They come from the corpus. Now, we would like to build a case for parameter projection. Wordnet dependent parameters depend on the graph based structure of the wordnet. Corpus dependent parameters depend on various statistics learned from a SenseMart corpus. Both these tasks require constructing a wordnet from scratch, collecting SenseMart corpora for multiple languages, and these tasks are tedious and expensive. So, the question we are asking is, can the effort required in constructing semantic graphs for multiple wordnets and collecting SenseMart corpora in multiple languages be avoided? So, these ideas are based on a novel synset based multilingual dictionary. This was published in Global WordNet Conference 2008. The authors are mentioned here: Rajat Mohanty, myself, Prabhakar Pandey, Shraddha, and so on. So, unlike traditional dictionaries, synsets are linked, and after that the words inside the synsets are linked. If we look at this one row from the dictionary, the multilingual dictionary, this row is the concept of a youthful male person. This is expressed by the word boy and male child in English. This concept is expressed by the words ladka, balak, bachcha in Hindi. These are also expressed by the words mulga, porga, por in Marathi. Now, Hindi is used as the pivot language, the synsets of all languages linked to the corresponding Hindi synsets. The advantage of this representation is that the synsets in a particular column automatically inherit the various semantic relations of the Hindi wordnet. The wordnet based parameters thus get projected. So, if we look carefully, we see that each column in that multilingual dictionary is nothing but the wordnet of that language. So, this whole column is the English wordnet, this is Hindi wordnet, this is Marathi wordnet, and all the synset IDs are placed in alignment with each other. Then within a particular row, the words are linked to each other. For example, boy can be linked to ladka, also it can be linked to balak, bachcha, etc. But these things capture what is called the register. Now, suppose the setting is informal, then the word boy may be linked to the word bachcha, okay, with less weightage, because maybe the discourse setting is such that the informal sense of boy is not very frequent. So, the main point being made here is that the concepts are linked, and within the concepts the words are cross linked, internally linked. The same notions are expressed here. If we take the Marathi words mulga, porga and por, then por is an informal word in Marathi, chora is an informal word in Hindi. So, a linkage is established from por to chora. The word porga, mulga in Marathi are more formal, and they are linked to the word ladka and balak in Hindi. For English, the word boy links to ladka and balak. So, this is a novel concept based dictionary where the concepts are linked and within them the words are linked. This produces a very rich lexical network. The concepts are linked and within them words are linked. So, this becomes a very rich structure of word linkages, and from that one can very easily create programmatically a bilingual dictionary. Okay. Once this rich structure is in place, various mappings can be established between the words. Proceeding further, this kind of sense smart corpus is used for words and disambiguation. The training of the system, words and disambiguation system, is done by means of this kind of sense marking. And here we see that the wordnet IDs are placed alongside the words. Imarat, for example, has many senses, but in the context that is shown, the ID is 11502. This is a particular sense of Imarat. Kala in the sense of art, kala in the sense of art is highly polysemous. In this particular context, the ID is 11642. So, this is the way the sense smart corpus is built, and this example comes from Marathi. Now, we take an example to understand the concept of parameter projection using the multidict. The parameter probability of the sense given the word is a highly important parameter. This is the first parameter under discussion. One can see that this particular parameter has to come from sense smart corpus. We have to count the frequency of the sense given the word. Let us take the word sea, let us take the word sagar in Hindi, which has these two senses, water body and abundance. The second sense is metaphorical, Gyan ka sagar, sea of knowledge. This sense ID is 2650 and it maps to the word samudra, water body sense in Marathi. The abundance sense is linked to the word sagar in Marathi, again with the sense of abundance. The sense ID is same in both cases. 2650 for the water body sense both in Hindi and Marathi. The sense ID is 8231 in Hindi and Marathi for the metaphorical sense of Sagar. Now, how will the probability water body sense given Sagar will be calculated? This will be calculated by a frequency count. We will see how many times does Sagar appear with the sense of water body. Okay. This will be divided by the number of times the word Sagar appears, assuming Sagar has only two senses, water body and abundance. And if we take all possible senses of Sagar, this will be exactly equal to the number of times the word Sagar appears in the corpora. So, water body sense of Sagar in the numerator, the number of times that happens divided by the number of times Sagar appears with water body and the number of times Sagar appears with abundance. This sum is equal to the number of times the word Sagar itself appears. Now, if we use the cross-linked Hindi word, we get P water body given Sagar as water body and samudra appearing together divided by water body and samudra appearing, and Sagar and abundance appearing together. So, in general, the probability of a sense given the word of a different language different from Hindi is equal to the sense and the cross linked Hindi word appearing together divided by different senses with cross linked Hindi word appearing in the corpus. So, I suppose it is clear what we are discussing. We want to calculate the water body sense of Sagar in Marathi, okay, but we do not have training corpus of Marathi which is sense marked. Suppose now this will be equal to the water body sense of Sagar divided by the number of times Sagar appears, or divided by the number of times Sagar appears as water body and Sagar appears with the sense of abundance. So, we will obtain the count from the cross linked Hindi word. We will see the cross linked Hindi word for Sagar, and we will see in how many times it appears in the sense of water body in the Hindi training corpus. How many times does it appear in the abundant sense in the Hindi sense mark corpus, and from this we will be able to estimate the probability of the Marathi word in a particular sense. Now, does this procedure work? Let us look at some data. The Marathi word is Kimat, which has two senses, worth and price. Marathi word is Rasta, which has two senses, road and route. Marathi word is Thikan, which has the sense of land site or place and the sense of home also. Now, we actually had some sense mark Marathi corpus, and when we calculate P s given the word, P sense given the word from Marathi corpus, the worth sense of Kimat comes with the probability of 0.684, whereas the price sense comes with the probability of 0.315. If we use the Hindi sense mark corpus for obtaining these values through projection and cross linking, then we get the probability values as 0.714 and 0.285. I hope it is clear as to what is going on here. the word Qimat is examined for its correspondence with the Hindi word in the Hindi SansSmart corpus, and the cross-linked Hindi word is obtained from the multi-dict. So, this cross-linked word appears in the sense of worth how many times in the corpus? That is the question asked. And the cross-linked word in the sense of price, how many times does it appear? The cross-linked word counts are found from the Hindi SansSmart corpus. The ratios are taken and we find the probability values. So, we find that the sense distribution actually obtained from Marathi corpus is not very wide of the mark compared to the sense distribution in the Hindi corpus. Same is the case for Rasta, the Marathi word Rasta. The sense distribution is 0.164 for roadway, and road or route sense has the probability value of 0.835. If we use projection from Hindi, then the distribution is 0.209 and 0.770. Similarly, for Thikan, the home sense has a distribution of 0.037 and 0.962 for land, site or place. When seen in the Hindi corpus, this distribution is 0.878 and 0.12. So, comparing the columns, we find that the values are not wide of the mark compared to the actual values. We also did a calculation based on KL divergence and Spearman's correlation coefficient, and we found that the KL divergence between the distribution learned from Marathi corpus and the distribution learned from Hindi corpus comes out to be 0.29, which is not very large. So, Hindi's the probability distribution from Marathi corpus, probability distribution learned from Hindi corpus are not very distant from each other. Also, the correlation coefficient is pretty high between these values. For Hindi Bengali, the values are more striking. The KL divergence is only 0.05 between the probability distributions, and Spearman correlation coefficient is high, which is 0.82. So, there is a high degree of similarity between the distributions learned using projection and those learned from self corpus. So, this shows the same statistics for a number of words. Now, we take the discussion to co-occurrence parameter projection. What co-occurrence parameter is again an important parameter for Warson disambiguation. Within a domain, the statistics of co-occurrence of senses remain the same across languages. This is our main foundational observation. Co-occurrence of the synsets cloud and sky is almost same in Marathi and Hindi corpus. We have few more examples. We take the synset rope, ropte, which is a small bush. The co-occurring synset is jhar, vriksha, taruvar, dhrum, taru, padap, the sense of tree. Now, the probability of co-occurrence as learned from sense tract Marathi corpus is 0.125. Probability of co-occurrence as learned from the sense tract Hindi corpus is 0.125 again. Megh, abhra, which is the sense of cloud in Marathi, has a co-occurrence of value of 0.167 with akash, abhar, ambar, the sense of sky. From Marathi corpus, the co-occurrence value comes out to be 0.167. When we see it in the Hindi SansSmart corpus, it comes out to be 0.154. The final example is Kshetra, Ilaka, Bhukhand. a geographical area. We examine its co-occurrence with travel. This co-occurrence value comes out to be 0.0019 when learned from Marathi corpus and 0.0017 when learned from Hindi corpus. So, some more words are tabulated here: Sita, Siya, Janaki, which is a mythological character in the famous epic Ramayana, and it has co-occurrence with Ramayan, Sita, Motha, Hindu, and so on. And the distributions are identical whether they are learned from Marathi corpus or Hindi corpus. So, based on these 5 parameters which are critical for words and disambiguation, we have come up with an algorithm for words and disambiguation. So, this algorithm we call IWSD, iterative words and disambiguation, and the algorithm makes use of some notions in Hopfield neural network. This is shown in the slide here. The scoring function is motivated by the energy expression in Hopfield network. The winning sense is obtained through a argmax computation by the scoring function. So, first we give the algorithm, we tag all the monosemous words in the sentence, we iteratively disambiguate the remaining words in the sentence in increasing order of their degree of polysemy. At each stage we select that sense for a word that maximizes the score given by the equation below. The scoring function is as follows: VI's are the most important parameters. VI's are probability of SI given the word, the ith sense of the word given the word. J is the set of disambiguated words. Then theta I is a parameter which captures the belongingness to a dominant concept SI. Wij captures the influence of the neighboring words. So, it is a product of 3 terms: corpus co-occurrence between SI and SJ. It is 1 by wordnet conceptual distance between SI and SJ and multiplied by 1 by wordnet semantic graph distance between SI and SJ. So, clearly as the conceptual distance or semantic distance increase, the strong association between the senses SI and SJ reduces. The strength of the association reduces. So, this is motivated by the energy expression in Hopfield net. These are the correspondences. The neuron corresponds to a scene set, self activation of the neuron corresponds to corpus sense distribution, weight of the connection between the 2 neurons corresponds to weight as a function of corpus co-occurrence, and wordnet distance measures between the scene sets. We have also used a modified page rank algorithm as a scoring function, just to compare the performance of our algorithm with the page rank based words and disambiguation. The reason is that the algorithms are very similar. We first disambiguate monosemous words, then disemous words, then trisemous words, and so on. So, the modification to the page rank based WSD as given by Radha Mihalcea is as follows. Instead of using the overlap in the dictionary definitions as edge weights, the wordnet and corpus based parameters are used to calculate the edge weights. The expression here shows the values for Wij, which is measured in terms of corpus co-occurrence, wordnet conceptual distance, wordnet semantic distance, and the probability values of the senses given the words. So, this is a recursive expression just like in page rank calculation. Score SI is expressed in terms of score Sj, and there is a damping factor D. The experimental setup was as follows. Tourism corpora in 4 languages were taken: Hindi, Marathi, Bengali and Tamil. Health corpora in 2 languages also were used, Hindi and Marathi. A 4-fold cross validation was done for all languages in both the domains. So, the first language is Hindi. The number of polysemous words is shown here. In tourism domain there are 50,000 words, and in health domain there are 29,000. For Marathi, in tourism domain there are 32,000 words, and in health domain there are 8,000 words. Bengali and Tamil have words only in the tourism domain, and the statistics are as follows: Bengali 9,000, Tamil 17,000. The number of censors in the multidict for Hindi are about 29,000, Marathi 16,000, Bengali 10,000 and Tamil 5,000. Now, we are ready to report the results of the algorithm with respect to various settings. First is our IWSD algorithm, the iterative WSD algorithm, which is trained on self corpus. No parameter is projected, and for Marathi we find that the precision is about 81%, recall is 80%, F score comes out to be close to 80%, more than 80%. Let us concentrate on Marathi for the moment. Now, trained on Marathi corpus, the accuracy values come out to be, the accuracy value comes out to be about 80%. When it is trained on Hindi and the parameters are reused for Marathi, then we find that the accuracy value comes out to be about 79%. So, this shows that there is a fall in accuracy, but the fall is not too much. Now, if we take a very similar algorithm, the page rank algorithm, which is trained on self corpora, then the accuracy value comes out to be about 79%. And if we use Hindi's sense mark corpora and reuse the parameters, then accuracy value comes out to be about 71%. So, what does it show? It shows that when self corpora is not used, there is a fall in accuracy of about 10 points in both IWSD and page rank algorithm. However, the values are still far higher than the wordnet baseline, that is, the algorithm chooses only the first sense of the wordnet independent of the context. So, there we find that the value is 58%, and there is a 20-point increase in accuracy on usage of self sense mark corpus, and about 10% increase in accuracy when Hindi sense mark corpus is used and parameter is projected. So, though there is a fall of about 10% in accuracy, the improvement is still very significant. The story is same for Bengali. In fact, here the parameter projection value hardly degrades. For Tamil, there is a 10% degradation, but the value is more than the baseline. When we made our observations in the health domain for Marathi, we found a 9% fall in accuracy when parameters are projected, but there is a 10% improvement in accuracy compared to baseline. So, some observations are IWSD performs better than page rank algorithm. There is a drop in performance when you use parameter projection instead of self corpora, but despite the drop in accuracy, the performance is still better than the wordnet baseline. The performance is consistent in both the domains, namely tourism and health. and one could trade accuracy with the cost of creating sense annotated corpus. So, this is an important point which is being made here. The point is that we are making use of the work done for one language for disambiguation of senses in another language. And this seems to have immense possibilities. Indian languages and many languages in the world like Turkish, Hungarian, Arabic and so on do not have too much of training corpus. So, if we can have sense smart corpora of some of these languages, then they can be used for disambiguation of words in other languages. The two things which are needed for these are as follows. We will write it here. The first thing that is needed, projection of parameters. So, sense disambiguation depends on projection of parameters. What they require in turn is what is called the multi-edict and some sense marked corpora. Multi-edict is nothing but aligned wordnets. Sense marked corpora are obtained from wordnet and chosen text in a domain. So, these ideas of parameter projection can be taken to active learning and semi supervised setting. What we do is that create some amount of training data and this is sense marked for one language. Now comes the interesting possibility. We have large amount of Marathi corpus and we have a small amount of Hindi sense marked corpus. So, the parameters are projected from Hindi to Marathi and that gives rise to creation of reasonably accurate Marathi WSD system. So, these ideas are fairly new and have been explored by us in detail and reported in top level research fora. So, with this we finish our discussion on Watson's disambiguation. We would like to summarize by saying that overlap based algorithm, supervised algorithm, semi supervised algorithm, unsupervised algorithm, these approaches have been discussed in detail. And finally, we have taken a look at the new direction of Watson disambiguation research, which is in presence of small amount of training corpus or no training corpus. However, a very strong requirement is that we should have aligned word nets for different languages, and though we say that the language is resource constrained, we still have to invest in creation of word net, which is by no means a small task. Now, an interesting question that arises is that what does Watson disambiguation research bring to us? Is it really crucial? Watson disambiguation is important for many applications like question answering, then accurate machine translation, then summarization and so on. But there is a view in natural language processing community that if we have lots of training data and capture many different contexts, then Watson disambiguation may not be required or may be required in a minimal amount. This is not really critical if we have large amount of training corpus and sophisticated machine learning algorithm. But this is a debate which is going on in the natural language processing community, and only future developments will show where the truth lies. Next, we will discuss parsing.